Hi everybody, I'm Oscar Navarro.
I'm Kayla Reyes.
I'm Andy Ye, and we are the RISC-V soft processors and sponsored by Lattice and Michael. Lattice proposed a project wanting to look into Berkeley's RISC-V solar processor and see possible benefits by comparing it to their existing microcontrollers. Berkeley's solar processor runs on a RISC-V instruction set architecture. However, it was intended for educational purposes, so it is a tethered emulator, meaning that the processor needs to be connected to a host PC with a full OS to function. We need to untether it for a standalone product, and by untethering, we would lose communication between the two sources, such as losing I/O and debugging capabilities, and we cannot stream in instructions from the host into Solar's memory.
So the goal of our project was to untether the solar processor and implement it in Verilog so that it could be a standalone soft processor and targeted to Lattice's FPGA to ECP5. But as Andy mentioned, by untethering it, we lose the ability to communicate between a host PC and the core. So our first goal of the project was to restore the ability to load instructions into the processor's RAM. And we could do this by replacing the original scratchpad memory with Lattice's embedded block RAM. And from there, we could use Lattice's software tools to load in a hex or binary file straight to the memory. And our next goal was to add our own basic I/O capabilities so we could see output from a program being run on the processor. And finally, we needed to make our own build tool flow that allowed us to write our own C programs, compile it using RISC-V compilers, and format it into a hex file that was compatible with Lattice's RAM.
Keeping these goals in mind, we began with unpipelined asynchronous processing. By familiarizing ourselves with its structure, we better understood the mechanics of the core and simplified the disconnection of the emulator. After disconnecting the emulator, we then had to remove the native scratchpad memory unit, which was too large to fit onto the FPGA. Instead, we substituted it with Lattice's distributed RAM, which allowed us to simulate the single cycle processing.
Next, we move on to the three-stage core, which is pipelined and natively uses synchronous RAM. This is very important as it serves as our baseline to understand how a pipeline core handles instructions. This was a major step for us as we attached the embedded block RAM. Also, the first core we put onto the FPGA and used Reveal to record waveforms on the physical device.
So once we understood how the three-stage worked, we moved on to the five-stage core, which is a more complex pipeline and is natively built to work with asynchronous RAM. The five-stage also features full bypassing to handle read after write data hazards, which means that at every stage of the pipeline, the core is able to take data, send it over to the register file to be used for upcoming instructions. So once we got the asynchronous version of the 5-core working, we wanted to switch it over to use synchronous RAM. This is because the ECP5 features a large amount of embedded block RAM, and by using this, we saved on a lot of lookup table resources. However, the EBR could only be used synchronously, so we needed to modify the 5-stage to handle this. And by switching over to SRAM, we ran into a few challenges. The first was simply integrating the SRAM, meaning we need to understand fully the core I/O and the SRAM's I/O to make sure that those were responding correctly to each other. And we need to maintain the same functions as the original memory, such as having subword access. So the original 5-stage core expected data access and data output, memory access and data output to occur within the same cycle. And this caused problems during our instruction fetch and during our memory stage. So to fix our instruction fetch stage, we had the core access fetch data for the next instruction while processing the current instruction. And to fix the memory stage, we had the core access memory during the execution stage so that data was ready by the memory stage. Now our next challenge appeared when we modified the instruction fetch stage. This is because we modeled the instruction fetch after the 3-stage core's instruction fetch stage. after reviewing other 5-stage pipeline architectures, we realized we needed to add a delay slot to handle the extra stage between a branch jump, between the branch being fetched and the branch being executed.
We have our central logic component that lets us choose between different peripherals. Our core writes to the address decoder, which consists of 3 muxes. The lower address range writes back into RAM. The middle address range writes to GPIO connected to LEDs, and the upper address range writes to UART, which we can send ASCII characters out onto a physical pin.
In order to use our toolchain, we developed, keeping these peripherals in mind, we developed a toolchain that would allow us to take an arbitrary C program and convert it over to hex. Organized into a makefile, we we first start the pipeline by taking a compiled program using the RISC-V GCC compiler, which excludes standard libraries and extracts the main function's binary. The resultant binary is then converted over to hex, which is with the proper dimensions. Following, then it's processed by a Python script that removes any padding, and it outputs a file to be loaded onto the processor. Here we see the actual LED peripheral showing the resultant C program run through the tool flow. And here we have the UART with the actual C program running through the tool flow as well.
So at the end of this project, we have 3 soft cores, a 1-stage, 3-stage, and 5-stage, that are ready to be compared to Lattice's Miko 32, and they're built specifically for the DCP-5. We've also added our own memory mapped expansion bus that allows us to write to RAM, to GPIO connected to LEDs, or through a UART. And these peripherals pave the way for more advanced I/O in future iterations. And we also have